started. Our first speaker here, I'm very excited to introduce Tom Beale. As Ricardo alluded to yesterday in his talk, Tom's been doing a lot of work with p.d.es. You're talking about some work with Svetlana? Is that
yes, right? Yes.
I myself, another kind of, every time I have some questions about boundary integral methods, or I'm like, has this stuff been done before? I go in the literature and find some beautiful work by Tom. So it's a pleasure to have you and welcome you to tell us today about computing nearly singular surface integrals.
Thank you for your generous introduction. I'm glad to be part of this nice event. I think I'll use the pointer here. Will that be okay? No one will.
Better boss.
Yeah. So I'm going to talk about two numerical methods. The first is the more familiar to people here. Svetlana and I have worked on computing surface integrals in 3D that are determined by harmonic functions or Stokes flow. And the emphasis is on evaluation near the surface. We've already heard that's the hardest case. To do that, we regularize as in the MRS, and then we try to make the regularization higher order in order to better control the discretization. So we have a recent paper, and as I promised yesterday, our methods are easier than they used to be. The second topic is a method for solving p.d.es on surfaces. It uses two-dimensional Cartesian grids. I don't know of an easier method for solving p.d.es on surfaces. And the heart of it is a clever way to discretize the surface introduced by Ying and I'm sorry, I forgot what the WC stands for Wang. Somebody knows if he wants to tell me.
During the talk.
Yeah. So as examples, let's use the familiar single layer potential for a harmonic function. And of course, the Stokeslets integral. I also use the stresslet, but I don't get into those other exotic things that were mentioned yesterday. So we say an integral is singular if y is on the surface and nearly singular if it's off the surface but nearby. Uh-oh, is this my third? No, I went too far. Okay, so here's how we regularize. Now, most of you are used to regularizing by introducing a blob to replace the delta function. But here our attitude is we have an integral kernel to start with, so we'll modify that directly with a factor s of r over epsilon. S is sometimes called a shape factor in some other work. Now, if you aren't used to this, suppose we take 1 over r and replace it by 1 over square root of r squared plus epsilon squared. We can rewrite that as 1 over r times this function s. Now, our choice of s is the error function, which is the integral of the Gaussian. And it has great advantages, particularly in making it easy to compute formulas, as I'll be saying. When we do this, g epsilon is a smooth function. It's of order 1 over epsilon as x goes to 0 rather than going to infinity. The difference goes to 0 very rapidly for large x, so something like 6 epsilon, you can neglect it. Now, of course, to compute the integral, we have to discretize. And how many people have said so far the error is the discretization error plus the regularization error? Let's think of it this way, add and subtract. We have the exact integral we want to compute, subtract the sum with the epsilon in it, add and subtract. So we have two parts. The error in the integral from putting in the regularization before we discretize, plus the error in discretizing the regularized integral. And what we do here, I think, is an opposite strategy from what Dana talked about yesterday. Dana must be here. You worked hard on the quadrature part, and our work is on improving the regularization. Of course, we all know that if epsilon's too big, we have too much regularization error, and if epsilon's too small, we have too much discretization error, and we're stuck with that so far as I know. Let's think about what is the regularization error. First, assume y is a point on the surface. I forgot to say I'm integrating over x and evaluating at y, and I'm afraid that's opposite to what many of you are used to. But well, never mind. The error is the integral g epsilon minus g times some density function f. Let's do a sloppy calculation. Pretend the surface is flat. Identify it with a horizontal tangent plane. Do the integral in polar coordinates in the plane. Replace f of x by f of 0. So then it greatly simplifies the theta integral we all know. F of 0 comes out. Now, it's important that we could rescale this integral so an epsilon comes out, and we see that the leading error is first order and proportional to f of 0. This is sloppy, but if we do it better, we find this is correct up to order epsilon cubed. There's no epsilon squared. Now, when we know this, how can we use it? We have three choices. We know the error, so we can subtract it out. Harder cases, we don't know it exactly. Suppose we know the error is order epsilon, then we can extrapolate Richardson extrapolation, use 2 epsilons. The third choice is we could replace the ERF by a related function so that this integral is 0 instead of what it was. And this is very close to an argument that Dana gave yesterday. We can, there are modified formulas like this for other kernels. Now let's talk about the nearly singular case. Suppose y is near the surface but not on it. Why do we care? We could be solving an integral equation with several vesicles and they can influence each other. So we have a system of integral equations, and then we have to take that into account. That would be nearly singular. Another possibility is we might have a three-dimensional grid and we want to find the values at grid points near the surface. It turns out that once we have those, say for a harmonic function, it's routine to find values at all grid points, thanks to an idea from Anita Mayo some years ago. We formed the discrete Laplacian near the surface, which has nothing to do with the exact Laplacian, extend it to be 0 and then invert. If that was too fast, I can explain it more in person. I'm about to talk about an expression for the regularization error from analysis near the closest point. So if y is close to the surface, there's a closest point x0, and y is along the normal line from x0. So y equals x0 plus bn, where n is the normal. And that will come up in the next part. So u0 is the exact integral for the single layer, and u epsilon is our modified value. And we're still just talking about the regularization error. The local analysis tells us that u epsilon equals u0 plus a term proportional to epsilon times a certain definite integral that depends on b over epsilon. Remember, b is the distance from the surface. Then there's an x term with epsilon cubed. This is the integral. Maple can do it. We'll make a change of variables first, or we can do it by hand. These integrals are known. ERFC, that's the complementary error function. It rapidly goes to 0, so the integral's convergent. That's 1 minus ERF. Now, it's important. It took me a long time to understand when we didn't. For a long time, we used corrections to the basic kernel, but they got too complicated, and they're limited in how the order. So it took me a while to understand there was this kind of pattern. We know the i's, and we can compute u epsilon. So our unknowns are U0, C1, and C2. The constants depend on the particulars of the problem, and they're difficult to find. So let's take the attitude that we have 3 unknowns, and if we compute u epsilon for 3 different epsilons, then we get 3 equations and 3 unknowns, and we can solve for the unknown we want, which is U0. So that way we get one that's accurate to epsilon to the 5th before discretizing. When we discretize, well, we have to decide how epsilon's related to h. The h is going to be on a 3-dimensional grid. We could choose epsilon to be proportional to h. And if we're lucky, we see the predicted order of accuracy in simple problems. But we want a method that'll work for more general problems. So to be safer, we can choose epsilon to be a fractional power of h. That's so that epsilon over h increases as h goes to 0. And therefore, we're controlling the discretization better as we refine. Now, you're probably wondering, does it work only for the single layer? It works for other integrals, but we have to put them in the right form to apply the kind of analysis I talked about. For the double layer, of course, it's discontinuous across the surface. So we use this familiar identity first to subtract. And that way, instead of f of x in the integral, we have f of x minus f of x 0. So that reduces the singularity. And then it turns out we have the same pattern. With the Stokeslets integral, we have to use a subtraction that's well known. It's in Pozorkides' Little Red Book, among other places. Now I'll show you an example with Stokes flow past a spheroid. That's a case where exact solutions are known. So we write the velocity as the integral with the Stokeslet times the force. And to discretize the surface, we have a 3-dimensional grid, and the grid points are intersection points where z, on the surface where z is a good function of x and y. We have points I, h, j, h, z, plus the 2 other cases. And there's a nice quadrature rule developed by Jason Wilson. I can say more about it individually if you're interested. So now I'm going to show you errors. No nice pictures, just errors. We were lucky this time. If deltas, if the red lines have delta proportional to h. Oh, I slipped. I call epsilon delta, but I changed it to epsilon this week. I knew I would slip once. So that's why it's delta on the slide. And the red is the errors with delta proportional to h. The blue is errors h to the 4/5. The c's are not the same in the two cases. So it worked. And now I'll show you a prettier picture. This is a calculation Svetlana did with one of her undergraduate students. We have two spheres in Stokes flow. The viscosity on the spheres is different from the viscosity in the surrounding fluid. We can solve an integral equation on the two spheres for the velocity. And I'm delighted to say we see the right order of accuracy in the errors, and the colors indicate errors with successive refinement. We don't know the answer, so the errors are determined by the next refinement. Now, let's see. Do you know how much time I have?
We have plenty of time.
Great. So my second topic is, as I said, is a method for solving p.d.e.s on a surface. So you could imagine, for example, a vesicle cell and some chemical diffusing on the surface. This makes use of a discretization by Ying and Wang. I knew it would come to me. We use a three-dimensional grid. We choose points where the surface intersects the grid lines. We're going to call the points primary or secondary. There are reasons for having both. A discrete function will have independent values only at the primary points. The values of the secondary points we find from the primary points. And it's important that the primary points are well distributed. The surface has to be at least C2, no corners or edges for this to work. So here's the procedure for discretizing. Cover the surface by a three-dimensional grid of spacing h. Oh, I should have said more about the figure on the last slide. It's the same figure anyway. Here you can see this is a curve in 2D rather than a surface in 3D. You can see here we'd like to think of y as a function of x. It looks like the slope is less than 1. So we'd like to use the points that are filled in. But there's this other intersection point, and we have to make a decision at some point. So it should be a way of deciding that we use the filled in point and not the other one in this case. So keep that in mind. So cover the surface by a grid. Find the intervals where there's an intersection point, or I'll call it cut point. You could do, if you have a level set function, you could ask where does it change sign between two grid points. Now we find the cut points. We only need some good ones. We can avoid bad ones. I won't say more about that right now. Now, for each cut point, ask what's the closest grid point. You can see in the center here, our two points are both close to the central grid point. After we do that, for each grid point, it may have more than one cut point assigned. And we designate the closest one as primary and any other as secondary. You can see this could be phrased in terms of the normal. We're saying we want a point where the normal has a large vertical component. This is remarkably simple. There can be some tie cases, but they're not a problem. The primary points are quasi-uniform, meaning that they're spaced proportional to h within constants. So that's this great idea. Now, we do need some of the secondary points. So how do we, if we have a function with values at the primary points, we need to know how to get values at the secondary points. So now these points are labeled. This is a secondary point. That's a primary point. If S is a secondary point, it's associated with a primary point that has the same closest grid point. Then it looks like we should use quadratic interpolation to get a value at S from the value at P, Q minus, and Q plus. But there's a catch. We'd like to use this formula, but Q plus or minus might be secondary. We know P is primary, but the Q's could be secondary. So that means we really have a linear system of equations to solve. And it's a very nice system. The MSS part is sparse. So I just tell MATLAB to solve it, no problem. Now, we want to think how to apply this to a p.d.e. on the surface. When we evaluate some difference operator, we'll evaluate it only at a primary point, but some of the neighbors of the primary points might be secondary, and that's why we need at least some of the secondary points. Once we've done that, let capital E be the extension operator that we just described, or equilibration operator that gives us values at all the points from the primary points. So that's how we're going to do a differential operator. We might have a p.d.e. like du dt equals lu, where L is some differential operator. We have to decide how to form the difference operator. We're always going to use coordinates of the form z is a function of x and y, or the other two cases. We don't need anything other than that. So we'll need three versions of LH. So here I put in probably too much notation, but as I said before, if we're going to, well, discretize in time by an Euler step, so the new value of u will be the old value plus this update where we first apply the difference operator to the old u, then do the extension times the time step k. So that would be the idea. So if we talk about diffusion on a surface, the prototype diffusion operator is the Laplace-Beltrami operator, which is the analog for the surface of the ordinary Laplacian. It involves the metric tensor. This is actually the inverse metric tensor. So we had to learn some undergraduate differential geometry. Fortunately, these G's are easy to express in terms of the simple coordinates we're using. What's my time now?
Few minutes.
Few minutes. Okay, so this is the discrete, no, I'm sorry, this is the Laplace-Beltrami operator. Now, we all know how to discretize Laplacian, but now we've got some mixed derivatives like dx, dy. How do you do that? Well, you second difference along the diagonal. And actually, there are two versions depending on the sign of G12. Now, if you've heard of an M matrix, identity minus the ordinary Laplacian is an M matrix. That's a way of expressing what's good about it. I said we could use the forward Euler method, but we might decide to use the backward Euler method, then we need to invert this matrix. Now, I have had no trouble finding the inverse in practice, and in the test problems, I get second order accuracy. I'm not able to prove exactly that this matrix is invertible. It's almost an M matrix. If we didn't have the overlapping coordinate systems, then it would be with the choice I described. But I can't prove that it is. And I can't, in all my examples here, I find second order convergence, but I'm not able to prove convergence, which is very disturbing to me since I make my living as an analyst. We can also do transport on a surface. For linear transport, well, we want to use the tangential gradient of a function, which if you haven't heard of it, it's what you would think it would be. It turns out to have a nice simple expression in these special coordinates. I even did an example with the shallow water equations on a sphere, which could be the beginning of a model of the atmosphere. Now first of all, numerical methods are developed so they can be used. And I really hope you folks can make use of the methods I've described. So I'll end with some references. This is the paper for the first part of the talk. This is a very recent paper by Svetlana and her student. This is the paper about solving p.d.e.s, and this is the earlier paper from which I got the idea about the discretization. And besides me, you can talk to Han Zhou, who's an expert on this method. Thank you.
I'm understanding correctly, which is doubtful. In the first part of the talk, you calculate velocity with you calculate velocity with 3 different blob sizes to get super high order accuracy.
Yeah, we found that worked pretty well in our test problems.
Is that more efficient than just doing one calculation with a small blob size? Like always or sometimes? How do you know which is more efficient? You know,
I don't, but I know this is high order, so I know as you decrease h, it's getting better. I should have said that this extrapolation is good for points near the surface. It is not good for points away from the surface because the 3 equations to be solved become more or less the same thing because we're getting away from where the regularization matters.
So the first part, even when you regularize, you still have a nearly singular integral. So
yes.
You still have to do quadrature.
Yes.
Right? What kind of quadrature scheme are you using?
Yeah, I described it just briefly. Imagine you have a 3-dimensional grid and you project in the 3 different directions from points on the surface. So you get 2-dimensional grids, but they have to be combined the right way. Now, we could think in terms of a partition of unity on the surface. That would be a way to put them all together. But Jason Wilson had a better idea. Choose a partition of unity on the unit sphere, and now call the function phi. Instead of using phi of x, where x is a point on the surface, use phi of n of x, where n is the normal. So we're applying the partition of unity to the normal vector rather than to the points directly. And that has a great advantage. You don't have to know much about the surface in order to do that. Now, that works great when the surface is static, and that's the cases we've done. If you have a moving surface, then how well that, I mean, you'd have to decide how you're going to discretize the surface. And indeed, if the points become distorted, then the discretization error could be worse. And I've done some analysis. Roughly speaking, the discretization error is first order in H. Sounds terrible, but it's multiplied by something like e to the minus constant times epsilon squared over H squared. So I like that second factor because the larger epsilon over H gets, then the better the discretization is. So in a way, I'm surprised that it works as well as it does, but we've, in the tests we've done, it does.
Thank Tom again.